All right, let's talk about internal energy and temperature. In terms of internal energy, I'm going to give you a situation here since we've talked about forces and we've talked about work and we've talked about energy. If we look at a box, this particular box, being pushed across a surface of some sort, okay, at a constant velocity. If it's moving at a constant velocity, we know that the applied force and the friction force are equal to each other. So if we answer some questions, okay, is work being done on the block by the force applied? Well, if it's moving, which it is, it's at a constant velocity, work is force parallel to the displacement. So yes, we can assume that work is being done by the applied force. Okay, and if work is done, basic definition of work is the transfer of energy or a change in energy. So is energy being transferred to the block? Yes, it would be. It would be transferred there as heat. Okay, is the kinetic energy of the block increasing? No, because if it's moving at a constant velocity, then you're not increasing the kinetic energy, and you're not increasing the gravitational potential because we're not going to a new height. Therefore, all that energy, okay, all that work that you're doing is basically just going inside the block as what we're going to refer to as internal energy, or better known as heat, which gets the symbol Q. Okay, and again, I'm not exactly sure why they use Q, but they use Q. Okay, so this is kind of a picture of the molecules and what they would be doing. Before you're moving it, the molecules are fairly set in stone and they're just vibrating there nicely. They're not moving around very much. As you increase the heat, okay, or as you add more internal energy to it, those molecules move around further. So it says the molecules are moving faster and are further apart. So technically, internal energy is a combination of the total potential and kinetic energy of those particular molecules. Okay. All right. So the next thing, again, something that should be fairly easy to understand, is temperature. Temperature is a measure of how hot or cold an object is, and it's temperature that determines the direction of heat flow. In case you're not aware, always heat flows from hot to cold. For example, you can be nice and toasty warm, but if you step outside in the middle of winter in Wisconsin, your heat likes to escape into its surroundings, and then it cools you down as well. Things that you need to understand about temperature is that it is a scalar. I can guarantee you that in this particular class, you're going to be looking at it in terms of Celsius or Kelvin. This tends to be a fairly important definition, that the Kelvin temperature is a measure of the average kinetic energy of the molecules of an object. And why the Kelvin temperature is so specific, energy cannot be negative. Therefore, the Kelvin scale, 0 is the smallest number you can have. Therefore, it is effectively a measure of the kinetic energy of those molecules. Okay. I've drawn in here some equations that you should probably be familiar with, converting from Kelvin, or from Celsius to Kelvin, or from Kelvin to Celsius. These are going to be important to use. Just keep in mind that whatever degree Celsius you have, if you add 273, you'll get Kelvin. And I've given you a couple milestone points here. 0 degrees Celsius, you know, as freezing, at least the freezing point of water. That would be 273 on the Kelvin scale, which would make sense, because if this is 0 and we add 273, then there we've got the degrees Kelvin. And 100 degrees Celsius is known as the boiling point for water, which would be 373 degrees Kelvin. Now, I've thrown in here conversions from Celsius and Fahrenheit, just in case it pops up, something that perhaps you should be aware of. Okay, so let's talk about devices used to actually measure temperature. You know them as thermometers. Now keep in mind that temperature itself isn't really measured directly. You use some sort of device that adapts to changes in temperatures. And thermometers are examples of that. If you look at any alcohol thermometer of any sort, in it there's a certain volume of liquid at the bottom, so volume of alcohol, and as it heats up, the volume increases because the molecules of that liquid are moving faster and faster, and they get further and further apart. Now, depending on whatever fluid you have in here, it could mean you'd have a really, really long thermometer or a really, really short thermometer with tiny little markings. But that's essentially what it is. It's just an object that changes with temperature changes. And as long as you know a couple milestone temperatures like freezing and boiling, then you can kind of scale anything to really read a temperature, as long as it changes with temperature. Okay. Now, one last little thing here to talk about in this particular section is something called thermal equilibrium. This is where, if you put a hot and a cold object together, eventually they settle at a certain temperature. So if I have two blocks that are, one's freezing and one's boiling, essentially, or at those temperatures, and I put them together, eventually they will end at some midpoint. So this is a perfect example. I'm saying perfect not because it's the best example to use, but this is in an ideal situation. If you had two blocks of equal mass and they were made out of equal material, and one was at 0 and one was at 100, and you put them in contact, ideally, if none of that energy goes off into the atmosphere or anything like that, this one should end at 50, and so should this one. So the key part of this is, okay, well, which way did the heat flow? Well, this one got hotter and this one got cooler, so the heat flowed this way, always from hot to cold. Okay. Now we're going to go over a bunch of problems with this after we've learned about specific heat and latent heat, but those are that's an important concept coming up.